The entropy of a black hole is proportional to the area of its event horizon, the surface within which even light cannot escape the gravity of the hole, especially the hole with a horizon spanning a Planck's area as a by 4 units of entropy. The Planck's area, approximately 10 to 66 square centimeter, is the fundamental quantum unit of area determined by the strength of gravity, the speed of light, and the size of quanta. Considered as information, it is as if the entropy were written on the event horizon with each bit, each digital 1 or 0 corresponding to 4 Planck areas. A tale of two entropies. Formal information theory originated in seminal 1948 papers by American applied mathematical Claude E. Shannon, who introduced today's most widely used measure of information content, entropy. Entropy had long been a central concept of thermodynamics, the branch of physics dealing with heat. Thermodynamics entropy is popularly described as the disorder in a physical system. In 1977, Austrian physicist Ludwig Boltzmann characterized it more precisely in terms of the number of distinct microscopic states that the particles composing a chunk of matter could be in while still looking like the same microscopic chunk of matter. For example, for the air in the room around you, one would count all the ways that the individual gas molecules could be distributed in the room and all the ways they could be moving. When Shannon's cast about for a way to quantify the information contained in, say, a message, he was led by logic to a formula with the same form as Boltzmann's. The Shannon entropy of a message is the number of binary digits or bits needed to encode it. Shannon's entropy does not enlighten us about the value of information, which is highly dependent on context. Yet, as an objective measure of quantity of information, it has been enormously useful in science and technology. For instance, the design of every modern communication device, from cellular phones to modems to compact disc players, relies on Shannon entropy. Thermodynamic entropy and Shannon entropy are conceptually equivalent. The number of arrangements that are counted by Boltzmann's entropy reflect the amount of Shannon information one would need to implement any particular arrangement. The two entropies have two silent differences though. First, the thermodynamic entropy used by a chemist or a refrigeration engineer is expressed in units of energy divided by temperature, whereas the Shannon entropy used by a communication engineer is in bits, essentially dimensionless. The difference is merely a matter of convention. The thermodynamics of black holes allows one to deduce limits on the density of entropy or information in various circumstances. The holographic bound defines how much information can be contained in a specified region of space. It can be derived by considering a roughly spherical distribution of matter that is that is contained within a surface of area A. The matter is induced to collapse to form a black hole. The the black hole's area must be smaller than A, so its entropy must be less than A by 4. Because entropy cannot decrease, one infers that the original distribution of matter must also carry less than A by 4 units of entropy or information. This results that the maximum information content of a region of a space is fixed by its area, defies the common sense expectation that the capacity of a region should depend on its volume. The universal entropy bound defines how much information can be carried by a mass m of diameter d. It is derived by imagining that a capsule of matter is engulfed by a black hole not much wider than it. The increase in the black hole's size places a limit on how much entropy the capsule could have contained. This limit is tighter than the holographic bound, except when the capsule is almost as dense as a black hole. In which case the two bounds are equivalent. The holographic and the universal information bounds are far beyond the data storage capacities of any current technology, and they greatly exceeds the density of information on chromosomes and the thermodynamic entropy of water. Even when reduced to a common units, however, typical values of the two entropies differ vastly in magnitude. A silicon microchip carrying a gigabyte of data, for instance, has a Shannon entropy of about 1010 bits. One byte is 8 bits, tremendously smaller than the chip's thermodynamic entropy, which is about 10,023 bits at room temperature. This discrepancy occurs because the entropies are computed for different degrees of freedom. A degree of freedom is any quantity that can vary. Such as a coordinate specifying a particle's location or one component of its velocity. The Shannon's entropy of the chips cares only about the overall state of each tiny transistor etched in the silicon crystal. The transistor is on or off. It is a 0 or 1, a single binary degree of freedom. Thermodynamics entropy, in contrast, depends on the states of all the billions of atoms and the roaming electrons that make up each transistor. As miniaturization brings closer the day when each atom will store one bit of information for us, the useful Shannon entropy of the state of the art microchip will age closer in magnitude to its material thermodynamic entropy. When the two entropies are calculated for the same degree of freedom, they are equal. What are the ultimate degrees of freedom? Atoms, after all, are made of electrons and nuclei. Nuclei are agglomerations of protons and neutrons, and those in turn are composed of quarks. Many physicists today consider electrons and quarks to be the excitations of superstrings, which they hypothesize to be the most fundamental entities. But the vicissitudes of a century of revelations in physics warns us not to be dogmatic. There could be more levels of structure in our universe than are dreamt of in today's physics. One cannot calculate the ultimate information capacity of a chunk of a matter or equivalently its true thermodynamic entropy without knowing the nature of the ultimate constituents of matter or at the deepest level of structure, which I shall refer to as level X. This ambiguity causes no problem in analyzing practical thermodynamics, such as that of car engines, for example, because the quarks within the atoms can be ignored. They do not change their states under the relatively being in conditions in the engine. Given the dizzying progress in miniaturization, one can playfully contemplate a day when quarks will serve to store information, one bit apiece, perhaps. How much information would then fit into our 1 centimeter cube? And how much if we harness superstrings or even deeper, yet undreamed of levels? Surprisingly, developments in gravitational physics in the past 3 decades have supplied some clear answer to what seems to be the elusive answers. The information content of a pile of a computer chips increases in proportion with the number of chips or equivalently the volume they occupy. That simply rule must break down for a large enough pile of chips because eventually the information would exceed the holographic bound, which depends on the surface area, not the volume. The breakdowns occurs when the immense pile of chips collapse to form a black hole. Black hole thermodynamics. A certain player in these developments is the black hole. Black holes are a consequence of general relativity. Albert Einstein's 1915 geometric theory of gravitation. In this theory, gravitation arises from the curvature of space-time, which makes objects move as if they were pulled by a force. Conversely, the curvature is caused by the presence of matter and energy. According to Einstein's equation, a sufficiently dense concentration of matter or energy will curve space-time so extremely that it rents, forms a black hole. The laws of relativity forbid anything that went into a black hole from coming out again, at least within the classical non-quantum description of the physics.